Welcome to physics class on total internal reflection TIR. In this total internal reflection, we will try to learn what is meant by total internal reflection, and is it the phenomenon of reflection or refraction? What are the prerequisites or required conditions to have total internal reflection? Then we will try to see what is meant by critical angle. Then we will try to move to data of the application part, and we will also try to see some applications. Okay, and then we will try to move to that part of some numerical calculations. In that way, we will try to have this today's class. Let's see what are the points to be discussed in today's class. Okay, the first one is, as I said, we will try to learn about the definitions, okay, of about total internal reflection. Then we will try to see what is meant by critical angle, then fish eye view. Okay, this fish eye view is also the application of the total internal reflection. Then again we will go to that application part, and then lastly we will go to that numerical assignment. Now, what are the prerequisite conditions to have this total internal reflection? That means the conditions which are required or essential for having total internal reflection is that light should travel from denser medium to rarer medium, and the angle of incidence must be greater than that of the critical angle. Then what is meant by this critical angle? Let's try to see what is meant by the critical angle. Now we know that when the incident angle is larger than the critical angle, total internal reflection will occur at the interface. That is a condition. But first, what is meant by this total critical angle? Let's try to know it. Now we know that when light travels from denser medium to rarer medium, the refracted ray bends away from normal, right? So when light travels from denser to rarer, we know that velocity of light in the denser medium is lesser than that of the velocity of light in the rarer medium. Now let's take it that the two media, okay, one is water and another is air. Water is denser, air is rarer. So let's try to have the path of the ray of light from denser medium water to the rarer medium air, like this. You see the path of the light ray it travels. Okay, the red dotted line is the normal angle of incidence is what? I1 for the first ray, and the angle of refraction is R1. Let's see from the light coming from the second source in this way, so that the angle of incidence is I2 and the angle of refraction is R2. We see that the angle of refraction R2 is more than that of the previous angle of refraction R1. That means when angle of incidence keep on increasing, then the angle of refraction also correspondingly increases. But there will be a certain particular angle of incidence for which the angle of refraction is 90 degree. That particular angle of incidence in the denser medium, we call it that as critical angle. This blue ray is the condition for that of having what? Angle of refraction 90 degree. You will see here I3 is equal to what? Critical angle. Why? Because the angle of refraction in that case is 90 degree here. See, you will see this is 90 degree. So that particular angle of incidence for which the angle of refraction here is 90 degree, that means this angle, we call it this angle of incidence as what? Critical angle. So that particular angle of incidence for which the angle of refraction in the rarer medium is 90 degree, we call it that as what? Critical angle. So now the prerequisite conditions we required for having that total internal reflection is that the angle of incidence must be greater than this critical angle C. So what happened when we take it for this next ray, okay, greater than that of the critical angle, then what happened? Instead of going light to the rarer medium there in the air, it will be rebounds back in the same denser medium, water. Okay, let's see the part. You try to observe it, this green ray. The angle of incidence is very much greater than that of the critical angle. Why? Because for this angle of incidence, okay, this will be greater than, you can take it this as I4. This I4 is greater than critical angle, right? So what happened? This I4, there will be also R4 here, and this R4 will be equal to what? Your I4, because by obeying your laws of reflection, okay, angle of incidence will be equal to what? Angle of refraction, right? So this green ray is for total internal reflection. Those conditions are fulfilled or not. Let's see. Light ray is going to travel from denser, okay, from denser to rarer. Yes, the first condition is satisfied. The second one is what? The angle of incidence. This angle of incidence is greater than the critical angle. It is also fulfilled. So what happened? All those prerequisite conditions of total internal reflections are satisfied, and so there will be what? Total internal reflection, right? In the next case, let's see for the next one, when light ray is passing for this also, then what happened? As this angle of incidence is greater than the critical angle, this will also have total internal reflections. So these two green rays, okay, as they satisfied the conditions for the total internal reflection to occur, they have what? Total internal reflection. Now that means these two rays are total internal reflection, those green one, okay. And we have also seen that critical angle. I'm just repeating again critical angle, the definition: the particular angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree. We call it that particular angle of incidence as what? Critical angle. Yes, let's see again the definitions, okay, of the critical angle. So if you want to note down, then you can note down by pausing the video. Otherwise, whatever I have told you, that is more than enough, okay. And the particular angle of incidence, I'm just repeating, I'm just reading it. The particular angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree is called critical angle. Now this is again the total internal reflection, the phenomenon in which the light is reflected back into the denser medium when a beam of light traveling from a denser medium to the rarer medium at an angle greater than the critical angle for the pair of transparent media is called total internal reflection. This is the definition for total internal reflections, okay. You need to put, while writing a definition, you need to put those conditions required for total internal reflection. It is a phenomenon of light, no doubt, in which light is reflected back into the denser medium when a beam of light traveling from denser medium to the rarer medium at an angle greater than the critical angle for the pair of media, okay, is known as what? Total internal reflection, right? Now let's see some applications, okay. Now for glass air interface, we know that the critical angle is 42. So at a critical angle, okay, angle of, say, angle of refraction is 90 degree. So by the law of refraction, we know that from the Snell's law that refractive index of the water with respect to the air, okay, not refractive index of air to water. So the diagram was like this. This was water, right, and this side was air, okay. That means this side is the what? Rarer medium, and the downward is denser medium. Light should travel from here like this in the denser medium, and this is the normal, okay, and your refracted ray is like this. So we have to consider that this is the second medium and this is the first medium. So from the Snell's law we know that refractive index of the second medium means what? Air with respect to the denser medium means water. This will be equal to sine of angle of incidence, that means this one. So sine of angle of incidence means R is critical angle. If the angle is this one is a critical angle, then the refracted light, okay, must be moving parallel to the interface, okay, like this will not be the one. So the angle of refraction will be what? 90 degree. Am I right? Yes. So what this sine of critical angle C, if I'm going to take it, then the angle of refraction is what? The 90 degree, right? Sine critical angle divided by what? 90 degree. Sine 90 degree is 1, we know it. So if you want to have, then it will be sine of critical angle, right? Then what happen? If you want to use it not like this, rather if you want to express it in terms of refractive index of water with respect to air, okay, so for if you want to write like this, then this should be taken reciprocal, right? So 1 by sine of critical angle. But this type of this type of refractive index of water with respect to air, the second, okay, with respect to air, that can be understood, air or vacuum. So we can simply write as refractive index of water. When I write it like this, that means it represents what? Like this or this same, okay. This is absolute refractive index. As this is also with respect to air, then this is also what? Absolute refractive index. Got it? So what happened? Refractive index is equal to sine r by sine I, okay, that will be equal to what? Your 1 by critical angle. Got it? So refractive index, that means absolute refractive index of a denser medium, times your critical angle will be equal to 1. Got it? So you can write it from here that critical angle, sine of critical angle will be equal to 1 by refractive index of the denser medium, rather absolute refractive index of the medium, okay. So reciprocal of the refractive index of a denser medium will be equal to what? Sine of the critical angle. So from this relation you can easily find out your refractive index. Either you can use it this one, okay, or you can use it this one, okay. From these two relation you can easily find out, okay, critical angle or refractive index. But in the next slide I will give you for critical angle also, if you know what the refractive index. This is the expression to find out what refractive index if you know the critical angle. Got it? If you know the value of C, and if you want to find out the critical the refractive index of the denser medium, then you can use this formula, okay. And similar to that, in that of the critical angle in the previous what equation, you can also find out critical angle if you know the refractive index, okay. It is here like this. Got it? The refractive index of water is 1.33. Then if you want to find out the refractive the critical angle for the refractive index of water 1.33, then what happened? Your critical angle comes out to be 48.8 degree. So it is about approximately about 50 degree. So if your angle of incidence is more than 50 degree, then naturally there will be what? Total internal reflection, okay, when light travel from denser medium to rarer medium. Got it? So if you want to see it, the calculation, then you can check it also here. From sine C is equal to this, okay, sine of 48.8, which is equal to 0.75, okay. 1 divided by 0.75 is what? 1.33, okay. It is also given here, see this one. So what happened, you can easily find out for the critical angle. So you can do it by using such formula, okay, to find out critical angle if you know the value of the refractive index of a denser medium, right? Now just these are the examples of the finding of your critical angle, okay, if you know the refractive index. Refractive index of glass can be taken as 1.5. 1.3 is also there for water. So if you want to find it out by using that relation, okay, you can easily find out the critical angle for glass as well as for water also by using that the previous, okay, same formula, okay. If you want to use it for what, refractive index, you can use it. Refractive index is equal to 1 by sine critical angle. Or if you want to find it out for that of critical angle, then you can use it this relation, C is equal to sine inverse of 1 by refractive index, like that, okay. Now next is what, this is about the what a fish eye view by drawing a ray diagram. Just I'm showing you here, see, okay, a shark is coming, so that this small fish will run away because he can see that that small fish can see that big shark very easily. So these are the what, fish eye view that can be seen. So you just see it again, I'm showing you again, okay. A light ray which is coming from the above the water, that can be also easily seen, okay. Its cone its cone of view is also here, okay. All those light rays coming from this portion, okay, it can be seen by the fish, okay. That means outside the water, okay, all those coming from this side also it can be easily seen, okay. That is why when we try to go near the water in the pond, okay, you may be going very quietly, but the fish, okay, inside the water can easily see you, okay. That's why they run away when you just go near them, right? Right. And moreover, it can be also seen for those objects coming, okay, like this by the shark, because due to that of total internal reflection, light coming from here, it will go to this and it can be easily seen by that small fish here. Got it? Yes. So let me show you again. See, so that shark coming, okay, it will be seen very easily and this small fish will run away like this, okay. Yes, these are the what the fish eye view, okay. I'm just giving you the idea with this diagram, okay. And it may be also asks the cone of view, okay, when light, okay, coming from the what, air to water, what will be the cone of view. Then if you are asking that cone of view, then here you will see from outside, okay, I'm talking about outside, not inside. So there is a cone here, it is just like a cone, okay. From outside, if the object is standing somewhere here also, that means it is outside, okay, the water. So whatever the ray coming from here, it will be also, it can be also coming like this, no. So this ray, okay, that will be the cone of view, this one. Got it? So if you are asking to find out the angle of this cone of, okay, that observation or cone of view, then you need to find it out this angle first, okay. This angle, double of it will be what, your angle of cone of view. Got it? So how to find it out this cone of view? Now that is very easy. Now suppose for example, you can have like this. Now if you are having that your point of observation is somewhere here at O, then you need to draw this as a normal, okay. Then what happen, a light ray coming from here, okay, this one, if it is in this way, right, then what happen, you can take it another one here as the what, normal, not here. you can take it normal here, and this angle is what, 90 degree. Okay, light ray which is coming here, it will be going in this way. Okay, so this is a refracted ray, you can say, and this is an incident ray. So this is the what, critical angle, right? So you need to find out this angle. Got it? So this angle is nothing but this is double of the critical angle. One C here, another C here. So if you can easily find out this critical angle, then double of it will be the cone of the angle, okay, of the view. So what happened if you want to find out this critical angle by using what? If you know the refractive index, then you can easily find out this critical angle. So double of the critical angle will be the angle of the cone of view. So this is your cone of view, right? So for that angle it will be what? Twice of C. So by using that relation of what, your critical angle is equal to 1 by sine of the refractive index, okay, 1 by sine of refractive index. You can find it out, your relation like this, refractive index is equal to 1 by sine of critical angle, like that. Got it? Or if you want to find it out that critical angle C, then it will be equal to what, sine inverse of, right, 1 by n. So by using this relation you can easily find out, right? Are you getting my point? So if you want to use it, this relation, then just to find out what critical angle C, then from this relation it will be what, sine C will be equal to 1 by n, like this, right? So your C will be equal to what, sine inverse of 1 by n, right? So if you can find out the reciprocal of the refractive index and taking the inverse of sine, then you will get it the critical angle. So double of this critical angle C will be nothing but this will be the angle of the cone of view of that, okay, observer which is inside the water, right? Yes. Now what did you learn? Critical angle, as I have just told you the expression, okay, it is coming up here that C is equal to sine inverse of 1 by n, like that. Total internal reflection occurs when a light ray tries to escape from a denser medium like that of water or glass to a rarer medium like that of air at an angle greater or larger than the critical angle at the interface, okay. uh, Fish eye view is an example of total internal reflection and refraction. Okay, we will try to see some of the what applications, okay, in the case of what this cold region, we call it that as looming. Looming is nothing but this is an illusion, okay, just like an illusion due to the what phenomenon of total internal reflection. Say, see, in the cold region like that of just above the water or sea, your ship which is floating on the sea may be seen somewhat raised or flying upward like this, okay. So this is the layer of the water free surface, I mean, and you may see that the ship has been little bit raised like this above the level of the water, okay. This is the level of the water. So you may see, okay, it may appears the ship to raise little bit, okay. This is due to the what total internal reflection. And another one is also there. See, in the case of the ship, how it is taken place, the actual position of the ship is here, but it seems that the ship is flying upward here because the light ray coming from the denser medium to the rarer medium like this, it seems that it is bended away and total internal reflection is having somewhere here, and to that person who is observing, the light ray is coming in this direction, so it may be seen, okay, to have that object somewhere here when you retrace backward like this, okay. So likewise, what happened in the case of the hot region like that of the heated rod surface, we may see that on the rod it seems to be somewhere there water like that, but it is not water because it is due to the total internal refraction in that hot, okay, air just above the tar rod. Okay, so that is known as mirage in the case of what hot region. Okay, it may be also in the desert that to a rider on the back of the camel, he may see that there is water or oasis in the desert, but when it go nearer and nearer, there will not be no more what that oasis. Okay, oasis means those pond, small pond like what water body in the desert. We call it that as at the desert we call it that as what total internal refraction. Due to total internal refraction we call it that as mirage. Okay, yes, the glittering or the sparkling of a diamond is also due to that of total internal reflection. When light ray enters, okay, then what happen, all the light rays due to that of dispersion, it will be coming out. Okay, and when it is little bit changing its position, then it seems it is sparking. So that is all due to what total internal re- reflection. Okay, and one important application of this total internal reflection is optical fiber. Optical fiber, this is just a fiber. Okay, it may be made of glass, but it must be what flexible. Got it? When you turn this total this what the optical fiber, if you twist it also, whatever the light that is entered, okay, at one of the opening of the fiber, it will go back. Okay, it will move back to like this. In this part it will move to the other end. Got it? If you make to pass or allow to incident red light also, it will pass it. If you allow another light ray like this also, it will pass. Okay, with the blue color I mean. So depending upon the different wavelength, depending upon the different what velocity, depending upon its different amplitude, we can have all those different light rays at the other end. Got it? So to know the structure of the optical fiber, this is made up of two transparent media. Okay, it may be of similar one or dissimilar one, doesn't matter, but the thing is that it should fulfill the conditions of those of the total internal reflection to occur. What are the prerequisite conditions? Light should travel from denser medium to rarer medium, and its angle of incidence must be greater than the critical angle, right? No? So what happened? There will be two transparent structure, one at the middle that is called as core, and this will be enveloped by another material which is known as cladding. Okay, and this cladding, when you compare with the cladding and the core, the refractive index of the core must be greater than that of the cladding. Cladding means surrounding envelope to this core. This is just like a cylinder. Okay, the core is just like a cylinder in this way, and your cladding is also just in the form of cylinder. It will envelop this core like this, in this manner. Okay, so what happened, the refractive index of core is greater than that of the refractive index of this cladding. Why? Because when light is allowed to incident onto this denser medium, then it will bend, it will try to go outside the what this core medium to that of the cladding medium. Okay, but as its angle of incidence is greater than the critical angle, then what happened, it will try to have this total internal reflection here, then it will try to move in this direction. Got it? So as this is only for the reflection, there is no absorption of light energy. Okay, so what happened, there will not be no what decrease in the light energy that is entered. That much amount of energy will be coming out at the other end, however long the optical fiber is. Got it? So this can be used in the communication. We call it that as optical fiber communication. It can be used for uh, transmitting signals from one continent to another continent by using this optical fiber. Okay, placed just underneath the ocean. Okay, we call it that as in intercontinental optical fiber communication. It can be used like that. Okay, so what happened when you compare it, the refractive index of the two material, the core material must be having what higher refractive index than that of the cladding. Why? Because this core must be of denser, okay, and the other cladding, I mean this will be what denser, and the cladding material must be of that of rarer medium when you compare with the core and cladding. Got it? So that is all about this optical fiber. And just to cover it, this core and cladding, we may call it that coat or plastic coating, we call it that as buffer coating. Okay, buffer coating here, like this. Got it? So with that, we will try to come to the end of this today's class. Thank you for watching my video.